we created our domain by placing 40 times 23, a grid of 40 times 23 particles in it. We gave a diameter to each of them and we gave the mass. We attribute to each of them a unit for the same value of xi 0.3. Now we need to start providing some parameters of the optimization method. So the method that will try to concentrate the xi only into the most important particles. If you read through the papers that are provided with the folder, you will see that the criterion is to try to place this xi, so this mass, the existence of the structure, into particles that most contribute to the stiffness of the structure itself. So try to make it as rigid as possible so that we will have to use the maximum force possible to deform the structure. If you read through the papers, you will see also what the meaning of these parameters is, each of those. The first parameter that we are giving here is the tolerance for the convergence method. As we said, the method will progressively move the xi from one particle to the other. I can open up this file here, so you see that you start with uniform distribution of xi in gray, and then progressively some areas become darker, meaning that they absorb the xi from the neighbors, which becomes whiter, so they are disappearing. Well, during this process, when does this process stops? Well, this process stops either when you interrupt it because you had enough, so you can just break a simulation manually, or when the change in xi, so in these existing parameters for any particle, is smaller than a threshold. And this threshold is given here. It's a very, very small value. So only if none of the particles will change its xi by more than 0.004 between one iteration and the next one in the optimization, then the code will stop. So this criterion is very strict. It's almost never going to be satisfied. So if you want it to actually stop, you better put a higher value here. But otherwise, I just want to let it run until I think that enough convergence has reached, and then I'll stop it manually so I can put a very small value here. Move is a parameter that also you will find described in the manuscripts. This tells you what is the maximum amount of xi that you can add or remove from any particle in one step of the optimization. Meaning that if you look, for instance, at the particle here in the middle, so let's look at the particle here. If you hover the mouse on top of it, you will learn later how to use this code when we will get the results. This is already peeping into the future when you will have the results of the simulation. But if I hover the mouse, let me increase it a little bit. If I hover the mouse somewhere here in the middle and check the value of xi down here, it will appear when I put the mouse there, you see that it starts from 0.3. And then if we do one step of optimization, so the step number 1, if we put look at the same particle, is again 0.3, nothing happened yet. But if we do another step, now we see it is 0.4, the xi value that is appearing down here. So this means that probably this particle wanted to increase its xi even more, because of course this particle is under the point of application of the load. Above a support is going to be very important for the stiffness, so it wants to attract as much xi as possible. But it cannot, because in the input file we gave as a constraint that the maximum change in xi for every particle at any step in the optimization is 0.1. Okay, so this is what this move is doing. It's trying the system not to go too fast. And it's usually a good idea to put a quite small value here because it can help convergence. If you put it too big, you can have some numerical problems. So 0.1 is a high value. Typically, I work with 0.01 or 0.02. Okay? But this is just to make the simulation faster. The higher this is, the faster the simulation goes, but there is the risk that it will not converge if it goes too fast. The next line is about filtering. Filtering is something that I will not explain in detail here. It's something that you find explained in detail in the first manuscript attached in the folder, in particular around equation 20, is this equation here. And in practice, what it means is this. It means that when you compute the sensitivity, that is this dc over dxe for the generic particle I, the sensitivity is not based only on the sensitivity computed on particle I, but it is also based on an weighted averaging of sensitivities for a number of other particles around it. And all the particles that are within a distance from this particle I, a distance called r min. So any particle that is within a distance r min for particle I will contribute in a weighted manner to its sensitivity. What does it mean? Well, you cannot understand it unless you read the papers, you understand what a sensitivity is, which is a measure of how much a particle contributes to the objective function that is minimized, or maximized. In this case, it's how much every particle I contributes to the stiffness of the structure. Okay, so it tells you how important a particle is for the stiffness of the structure. And the papers explain how you compute it, how the code computes it. When you run the code, you don't have to worry about it, but you have to tell the code whether you want it to use this averaging around the particle or not. The effects of this averaging are also described in these papers, so please read them. But if you decide to use the filtering, and I strongly recommend you to use at least a little bit of filtering, then you have to put filtering on here. Then what are the two attributes here? The first attribute is r min, is this distance from the center of a particle to catch the particles nearby, decide how many particles nearby you want to involve. And typically, what I suggest to do for the exercise that you're going to run is to put this value here slightly bigger than a diameter. So for a diameter of 3 millimeters we're using here, a value could be 3.1. This other parameter is called beta. You won't find a trace of it in the papers. This is just because the code implements a slightly more general version of this equation 20, which also has a beta factor. But if you put beta equal to 1, then you are going to use exactly this equation 20 that you have in the paper. So my suggestion for your example, put filtering on a value slightly bigger than a diameter and then 1. The next parameter of the optimizer that we are giving is how do we want sensitivities to be computed. And if you read through the papers again, you will see that there are two ways of computing sensitivities that are described in the papers themselves. One way is to use an approximate expression that is shown here in equation 16 in the first paper. Or you can use a more complete approach that is called numerical perturbation method that is described in the appendix of this manuscript. Now, in this paper here, in your examples, I strongly recommend you to always use the partial approach because it's precise enough. If you read through the papers, you understand that it is indeed sufficiently good and it is significantly faster to run compared to the brute approach or the numerical perturbation method approach. So use, please, sensitivity partial. Then there is a penalization power here. This penalization power is something that is the exponent that you use in this equation here, which I don't remember where it is in the document. Here. So equation number 12 in manuscript part 1, this is the penalty factor that you are applying to the stiffness. We'll see later what this stiffness is. If you read through the paper, you understand what it means, but this is a parameter that helps you divide the particles between those that eventually will have zero mass and those that will have xi equals 0 and xi equal to 1. And this penalization factor from the literature, and if you read through the papers, good value is 2, typically. So we use this exponent p equal to 2. So this p pow is the p in the equation 12. You want to know what it means, read the paper. Xi min, I mentioned that the particles will have their value of Xi bound between 0 and 1, but I told you actually it's not going to be exactly 0. It's going to be a small value greater than 0. Well, if you go to equation number 1 in the manuscript number 1, 2, 3, this is the description of the optimization problem. We are trying to minimize the cost function of Xi, that is this expression here. We want to keep as a constraint the fact that the fraction of particles, which is just the sum of Xi over all the particles, is equal to the average of Xi over all the particles is equal to 0.3. This F equals 0.3. In the end, we want 30% of the particles to be solid and the rest to disappear. So this is where we put the F. And this constraint on Xi is between 0 and 1, but actually we keep it to a minimum of Xi min. So this is where the value of Xi min is given. Typically 10 to the minus 3 is a good value, to sufficiently small to be close to 0, but also okay to avoid problems that you have when you put Xi min equal to 0. So if you were to put a 0 here instead of 0, 0, 1, then you would have numerical problems that are again described here in the manuscript. So read the manuscript, you will understand why you cannot put Xi min equal to 0, or why you shouldn't put it. Then this target F, this is exactly this F here, is how many particles in the end of the simulations do we want to have a mass equal to 1 or a Xi equal to 1, and how many particles then, 1 minus those will be the particles with Xi equal to 0. So we want 30% of the particles in the end to have Xi equal to 1, so this target F, which is the same as this F in equation 2 here, is going to be 0.3. Notice that we set this initial uniform 0.3 equal to this final one, which means that eventually, if we just do the sum of Xi over all the particles, it will be the same when you are here, where you have n particles with 0.3 each, that you have at the end here, where you have 0.3 times n particles with Xi equal to 1, and the rest with 0. It's always going to be 0.3 times n, the total, the sum of Xi over all the particles, okay? But you don't have necessarily to start with 0.3 here. You could start with an initial uniform Xi of 1, and then the code should still progressively reduce the Xi down to 0.3, down to the target. So this is eventually at the end of the simulation. This is at the beginning of the simulation, what is the value of Xi on each particle. This is at the end of the simulation, what is the fraction of particles that you want with Xi equal to 1. So this is what eventually the code will give you. Now, there are a few other parameters for the optimizer here, but before we get there, let's open a parenthesis on the interactions between the particles, because eventually, so far we have defined the geometry, we have defined particles, we have defined parameters for the optimization, but we haven't given any force, we haven't given any mechanical interaction within the particles, so as a mechanical system, it's not doing much yet. But now we will do the first step of defining the interaction forces and potentials between the particles.